Okay, so good evening and welcome to today's Asset Colloquium. Asset at TIFR stands for Advanced Science and Engineering. So good evening and welcome to today's Asset Colloquium. Asset at TIFR stands for Advanced Science and Engineering. So good evening and welcome to today's Asset Colloquium. Asset at TIFR stands for Advanced Science and Engineering. So good evening and welcome to today's Asset Colloquium. Asset at TIFR stands for Advanced Science and Engineering. So good evening and welcome to today's Asset Colloquium. Asset at TIFR stands for Advanced Science and Engineering. So good evening and welcome to today's Asset Colloquium.
Just mute everybody.
Ajith, can you hear me? Do you have any other device with you? Because when I mute, now it is fine. Ajith, can you hear me?
I can hear you.
No, there is a loop back from your. Now it is fine. Now it is fine.
I can hear you.
No, again it is coming up.
From your. Now
it is fine. Do you have two devices by chance? Do you have a cell phone connected?
No, I don't have.
Do you have two devices by chance? Do you have a cell phone connected?
No. Do you want me to mute for some time?
Yeah, but when I mute you, we are not getting that echo.
I can mute it for some time.
But when I mute you, we are not getting that.
Okay. But I don't have two devices. I have only one.
But did you open YouTube link also?
We are not getting that.
Okay. Yeah, that's fine. Okay. I hope now everything is fine.
But when he starts speaking, how you will do with this?
Sorry?
When he starts speaking, how will it work?
So Satya, maybe what you have to do as an experiment just now is to mute yourself and allow Ajith to speak. If that doesn't result in echoes, then we are good to go, right?
Oh, Ajith is muted. I thought he has. Ajith, can you unmute?
Yourself and allow Ajith to speak. If that doesn't result in echoes.
Yeah, now I have unmuted.
Oh, Ajith is muted. I thought he
has. No, now I have unmuted. Now I have unmuted.
Allow Ajith to speak. If that doesn't result in echoes.
Yeah, now I have unmuted.
Oh, Ajith is muted. I thought he
has. Now I have unmuted. Now I have unmuted.
Allow Ajith to speak. If that doesn't result in echoes.
Now I have unmuted.
Oh, Ajith is muted. I thought he has.
Now I have unmuted. Now I have
I think Ajith microphone speak up this voice and that echoing continuously.
I have unmuted myself and tested. Even that condition when Ajith was unmuted. Sorry, it gave problem.
No. It looks like Ajith speaker pick up this sound, and then it just echoing continuously. This going and to and fro.
The speaker, it shouldn't.
No, the microphone pick up this noise sound.
Ajith, are you using headphones or open?
No, I am not using headphones.
Pick up this noise sound.
Ajith, are you using? Can you try headphones? Do you have headphones?
No, I am not using headphones.
You are not using.
No.
No, can you use? Headphones? Do you have headphones?
No, I am not using headphones.
This is very strange. I never got this kind of problem. So Ajith, you don't have any YouTube opened, right? Locally? No. You have to unmute. We can't hear you now.
I have YouTube open. Maybe I will close it.
Please close. That's what I told you sometime back. You have to unmute. We can't hear you now. Did you close it?
Yeah.
Ajith, did you close YouTube?
Yeah. I have closed YouTube now.
Ah, perfect.
Is
Okay.
this okay?
Yeah. That is the one. That is the one which is short circuit. Yeah.
Okay.
Okay. So yeah, sorry for this technical glitches. Anyway, let me formally invite today's speaker. Ajith is an engineer G working at NCRA-TIFR
I was not.
from September
Yeah.
1988. Currently, he is the group head of the backend systems at GMRT. He is responsible for the development and upkeep of backend systems for the old system, the legacy, as well as the upgraded backend receivers. He completed his BTech in the Electronics and Communication Engineering from College of Engineering in Trivandrum in 1988. And obviously, soon after that, he joined NCRA. And MTech in Communication Engineering from IIT Mumbai later in 1999. He's of course involved in the GMRT project from the very initial planning and design phase of the legacy receiver. And these other areas of interest include the system level design and integration and testing, signal processing circuits, RFI cancellation schemes, and time and frequency standards and clock distribution and beamformers for phased array feeds. Today he's going to talk in fact is a continuation of the series that we are having on the upgraded GMRT. In fact, this is the third lecture in that series. He's going to talk on specifically on the backend signal processing. So over to Ajith.
Okay, Dr. Satyanarayana, thank you very much for arranging this series of talks. So in today's presentation, I will describe the backend signal processing system at GMRT, especially the upgraded GMRT receiver. So in today we will start with an introduction to the signal processing in general for array radio telescopes. Then we will go to GMRT and the upgrades done in the receiver system. And we will go in detail on the upgrades done in analog backend, digital backend, as well as the time and frequency standards at GMRT. And then we will look at some of the current development jobs being done in the labs of backend system, and finally conclude with a summary and some future plans for upgrades which we have. So whatever I am presenting now is a job done by a large group of engineers and technical staff. We have people who are experts in signal processing, GPU coding, RFI filtering, FPGA work, and we also have experts in computers, networking, and programming, and also people working on time and frequency standards and analog signal processing. So just to start with an introduction on array radio telescopes, as we know, the collecting area as well as the resolution of a telescope increases with, for a single dish telescope, increases with the diameter of the dish. So there is a limit to which one can improve the resolution for any single dish telescope. So because of the limitations of having a large mechanical structure, that way a fully steerable dish. So to overcome this, people use multiple antennas, and the signals from different antennas are combined to provide a map of the source structure. And the advantage here is that when you have an array of antennas, the resolution is actually decided by the distance between the two telescopes. So if the telescopes are a few kilometers away, you get a better resolution. And the total collecting area of the system will be equal to n times the aperture, the array of one telescope. So now coming to the backend for a array radio telescope. The backend system generally works in real time. So you will have multiple antennas, and the signals from different antennas come to the backend system, which is generally located at a common place. And it generates different outputs based on the requirement of the user. So there is interferometry output, beamformer output, spectral line outputs, as well as outputs which can be used for very long baseline interferometry. So all these are done in real time by combining signals from the different antennas in the array. So now coming to the radio interferometer. So in interferometry, what we do is for each pair of antennas, we collect the signals, and the signals are delayed so that they are all in phase, because they, as you see, the wavefront is here, and some antennas will be receiving the signals after a certain time delay. So that delay has to be corrected, and then the signals are cross multiplied and accumulated. So each of these pair of antennas give one Fourier component in the image UV plane. And when you have several antennas, like in case of GMRT, we have 30 antennas, we get several Fourier components instantaneously. But now, as the Earth rotates, the more and more Fourier components in the UV plane gets filled in. And after a few hours of observation, the image processing software does an inverse Fourier transform to get the original image of the source. So this is an example of GMRT. The image on the top, this is the UV plane coverage, instantaneous UV plane coverage for the 30 antennas. And after a few hours of observation, the more and more points in the Fourier components gets filled in the UV plane, and you get a much better coverage. So the array is basically optimized. The location of the antennas is optimized to get a uniform coverage in the UV plane so that the best results of the map are obtained. Now, coming to the beamformer, this is generally used for studying compact sources like pulsars. In this case, the signals from different antennas are added together, and there are two possible ways of addition. Either one can do an incoherent addition of power, or we can do a coherent addition. So there are two types of beamformers possible. And beamformers are also used for collecting data for doing very long baseline interferometry. So this image shows the signal processing done in case of a incoherent beamformer. So in case of incoherent beamformer, what we do is we take the voltages from each antenna, which is squared to get the power spectrum, and then the power spectrum is added to get a final output. So here, since the squaring operation is done, we are only bothered about the power, the scalar quantity, and hence the phase information is not important, and no need of phasing in incoherent array. So when we go for an incoherent beamformer, it gives a root of an improvement in sensitivity, and the beam width is of the whole array is equal to the beam width of a single antenna. So such arrays are usually used in doing large-scale pulsar search. And whereas in case of a coherent beamformer, the individual voltages from each antenna are added, and then a squaring of the final voltage is taken to get the final coherent output. So since the voltages are added here, we need to take care of the phasing at the before doing this addition. So a coherent beamformer basically gives n times improvement in sensitivity, and the beam width is narrower by 1 by n times. And since it is a narrower beam with a higher sensitivity, the coherent beamformers are more useful for studying known pulsars and for polarimetry. Now we will have a quick look at the GMRT and then go to the upgraded receiver. So GMRT, as many of you know, is an array of 30 antennas located at village Kodak. which is about 80 kilometers north of Pune and 160 kilometers to the east of Mumbai. This location is having very low radio interference because of hills on all the sides of in all directions. And the telescope is operational from 2001 and has been used by both Indian and as well as foreign astronomers. The GMRT array is basically a Y-shaped array with, out of the 30 antennas, 12 antennas are in a very compact 1 kilometer by 1 kilometer central area, and 6 antennas in each of the arms. So we have a western arm, eastern arm, and a southern arm, each with about roughly 6 antennas each. And the signals collected at each of these antennas are brought to the central station through fiber optic cables. And the backend system is located in the central station in the receiver side. There is a central electronics building where all the backends are located. So the the farthest antenna in case of GMRT is about 14 kilometers away from the central station. So by combining this, all these antennas in the array, we get roughly the resolution of a 28 kilometer dish antenna. So this is a block diagram of the upgraded receiver. So we have antennas collecting the signals, feeds collecting the signals, which are then passed through low noise front-end electronics, which was described by Suresh Kumar in the last week's talk. And then the signals are directly transported to the central station through broadband fiber optic cables. And all the signal processing and down conversion and digitization are done at the central station. So the upgraded receiver, the amount of electronics in the receiver at the antenna site is very less. So much easier to take care of the system as well as troubleshoot the system whenever there is a problem. So at the central station, the received signals are first passed through an analog backend, which does some frequency conversion, some band shaping, and then it goes to a digital backend, which does the digitization and the further processing and combining of the signals from the different antennas. We also have a time and frequency standard at the central station, which generates the required clocks and reference timing signals. So the operating frequencies of the upgraded GMRT are 120 to 260, 250 to 500, 550 to 900, and 1000 to 1500 megahertz. And at the back end, we have a facility of processing a maximum of 400 megahertz, or using filters, one can reduce the bandwidth to either 200 or 100 megahertz also. So now look at the improvements in the upgraded receiver compared to the legacy system. So the original legacy system was having 5 specific bands in the 100 to 1500 megahertz range, whereas the upgraded receiver gives a seamless frequency coverage from 100 megahertz to 1500 megahertz, where with only some frequency ranges like the GSM band not used because of the radio interference. And the instantaneous bandwidth improves by a factor of 10 from 32 megahertz in the old receiver to a 400 megahertz in the new receiver. The old the legacy system has a facility of dual frequency observations in 2 frequencies with frequency bands, and the new system also allows multi-frequency observations but using the same feed. The time and frequency standard in the legacy system is based on a GPS discipline rubidium, whereas the new system uses an active hydrogen maser based time and frequency standard. And the legacy system has power level monitoring at few stages, and the monitoring system has been improved in the new receiver with all the voltage, current, and all the environmental parameters and including the power levels and spectrum monitored at different stages in the receiver. A quick look at the backend specifications. It supports 30 antennas and 2 polarizations per antenna, and supports a frequency range of 100 to 1500 megahertz. And there is a gain adjustment stage in the analog backend, which adjusts the power level in steps of 0.5 dB. This is very important because we are tracking signals from different antennas, and there is a possibility of signals coming at different power levels. So one needs to equalize the power before we give it to the ADC for digitization. And we also have a 27 dB headroom in the analog backend. So this headroom is basically the normal operating power to the level at which the 1 dB saturation happens. So this is important to take care of any strong RFI signals which are coming, to make sure that RFI doesn't saturate the receiver. And
can I ask a question?
Yeah.
The gain adjustment that you have, is
Yes.
it because of gain variations in the pickup from each antenna?
Actually, it is more to do with the gain of the receiver. Up to
What
this.
I mean, what I'm asking is whether each antenna has a has variable gain which is varying because of drifts, etc. In which case you will have trouble when you're combining all the signals.
Are you talking of the feed, gain of the feed?
Yeah, that's correct.
Yeah. See, actually, most of the power which we receive here will be due to the receiver noise, right? And
Okay.
the amount of power picked up by the feed is going to be very limited, little.
Okay.
Yeah. And we adjust that total power to a similar level before it goes to the ADC.
Okay.
Yeah.
Okay. Maybe I can come back to this question later. Thanks.
Yeah.
So maybe if I could just comment as a clarification, this there is no automatic adjustment. So this is like a one-time adjustment, and mostly it's done because there will be some variation from antenna to antenna, number one. And number two, when you change the radio frequency band, for different bands, the power levels are slightly different. So you do need to compensate to bring it to the optimal for the digitizer. But it does not correct for drifts, and those drifts are generally small and not very important.
Yeah, thanks.
Yeah. So coming to the digital backends, the main specifications are frequency spectral resolution of 2K to 16K. And we also have a narrowband mode, which gives a resolution up to 100 Hertz. And it supports full stokes. And the beamformer, it provides IA, PA, as well as the voltage beam outputs. There are also other features in the backend, where like independent LO frequency selection for each polarization channel. So we can even have the 2 polarization channels operating at different frequencies, as well as there is a power equalization by using the gain adjustment and analog backend. And in the digital backend, we have a set of buffer user machines, so that the users can log in during their observations to check the signal quality without logging into the main host machines. There are also calibrated noise sources at different locations in the backend receiver to check the gain as well as for testing purposes. There is a spectrum monitoring, which cyclically checks the spectrum for each of the antennas and each polarizations, which is a 60-to-1 monitoring system. And also a monitoring system for the power levels at various stages in the receiver. Also the environmental monitoring system, which monitors the temperature and voltage current at various levels, the rack level, as well as the plug-in unit level, as well as room level is also provided. So coming to the analog backend, this is a very simplified block diagram of the analog receiver system. So here we have the first stage is a variable gain stage, which varies the gain in 0.5 dB steps from 0 to 32 dB. And then there is a filter bank for selecting the same RF filter which is used at the front-end electronics to improve the signal to noise ratio. And it goes through a frequency conversion unit which converts the frequencies from the RF to the baseband of 0 to 400 megahertz. And then it goes through a baseband filter bank which has a selection of 100, 200 or 400 megahertz. And there is a buffered spare GAB output also, which can be used for any testing or any future digital backends when it is developed. This is a more detailed schematic diagram showing the analog backend. So the analog systems are installed in aluminum chassis of different standard dimensions, and they are all fitted inside a plug-in module which goes into a 19-inch rack. So each antenna takes one sub-rack space. Both polarizations of same antenna fit into one sub-rack along with its receivers and local oscillator and the control and monitor units. So each antenna we have, each rack we have 4 antenna system, and a total of 8 racks are needed for the full 30 antenna GMRT receiver. These racks are RFA shielded racks and provides about 40 to 50 dB of isolation when the doors are closed. This is a test result for checking the different bandwidths in the analog backend. So as we saw earlier, there are options of 100 megahertz, 200 megahertz, and 400 megahertz. So this experiment is done by giving a 400 megahertz bandwidth signal to the analog backend and selecting the filters for 100, 200, and 400, and checking the spectrum at the output. Similar experiment is also done to check the power equalization. So this is the data from the different antennas without doing any power equalization as seen at the analog backend output. And after doing power equalization using this variable gain stage, the power given to the ADC is equalized to a about minus 15 dBm. The local oscillator for the analog backend is based on the ADF4351, which is a wideband digital synthesizer and covers the full frequency of GMRT. So just one synthesizer is enough to take care of one polarization channel, and it can be programmed through a serial interface, and frequencies can be selected. And it's a very low phase noise device, providing about 97 dBc per hertz at 1 kilohertz offset. And the reference input also can be programmed to different frequencies. In our application, we have programmed it to 10 megahertz as the reference, and we are using the Maser output as the reference. So this is the phase noise plot, phase noise measurement plot for the ADF based 4351 based local oscillator. So now coming to the digital backends, this is a very simplified block diagram of a digital backend. So signals coming from each of the antennas are digitized, and then they are passed through a course delay to correct the delays in each of the antennas, and then frequent FFT is used to channelize the signals, and then they go through fine delay correction. The course delay is used to correct the delays up to the clock sample time duration, whereas fine delay corrects at faster than the clock period. And then the signals between different antennas are shared, and then they are cross multiplied and accumulated to form interferometer output, and they are added in beamformers and integrated to get the beam outputs. So this is the actual implementation of the digital backend at GMRT. So the main systems are the ADCs and the FPGAs, which acquire the data and packetize the data from the antennas. Each of these ADCs are two dual inputs, so two antenna, two polarizations can be connected to one FPGA board, which does packetization of the digitized data and send them through two 10 gigabit links to a CPU server, which has two GPUs in each of the servers. So all further processing is done in the CPU GPU nodes. And also for doing the cross correlation, we need to share the data between the different compute nodes. So all this data sharing happens through this 40 gigabit InfiniBand switch. And once the processing is completed, the visibility data is collected in the visibility host, and there are 4 beam hosts to collect the beam outputs. So there are a total of 32 antennas and 2 polarizations, 400 megahertz bandwidth, and the maximum FFT is 16K. So with this, the total compute requirement for GWB, the digital backend, is about 10 teraflops. And the data rates from the input FPGA board to the compute node is 12.8 gigabits per second. And between the compute nodes for data sharing is about 12 gigabits per second. And the outputs data rates are 3.2 gigabits per second for the visibility output with a 16K frequency resolution. And beam outputs is about 1.6 gigabits per second for PA mode of 20 microsecond integration. And for the voltage beam output, the data rate is about 6.4 gigabits per second. So coming to the data flow, this shows the complete data flow in one FPGA and one CPU server and the GPU, which is installed in the CPU server. So the each FPGA has 2 ADC boards connected to it. So each ADC takes signals from 2 polarization channels of the antenna. Two channels, and they are digitized and passed through a FIFO, and they are packetized to 10 GB Ethernet packets within the FPGA, and then sent to the compute server, where they are unpacking is done, and then they are kept in shared memories, where the delay correction is done, as well as the data is time sliced. So one slice of the data it keeps for processing in the GPUs in the same machine, and the other slices it sends to the other compute nodes through the InfiniBand network. And the time slice to be processed in the same GPU goes through the FFT and phase rotation and MAC beamforming, and all this processing is done in parallel threads within the GPU, and they are then sent back to the server and then transferred to the host machine through the InfiniBand switch. This is a example of a 4-node system supporting 16 antennas, just to show the how the data sharing is done. So with 4-node, in a 4-node system, each node will be collecting data from 4 different antennas, and the data received from each antenna is sliced into 4 time slices, because we have a total of 4 compute nodes. And then all slice ones, first slices of all the nodes, all antennas will be shared to the node 1, and slice 2 will go to the second node, and slice 3 will go to the third node. So after the data sharing process is over, the node 1 will have the first time slice of all 16 antennas, node 2 will have second time slice, like that. So once this is done, the further multiplication, accumulation, as well as the beamforming within this first time slice or second time slice is very easy, done within the same node, and then can be transferred to the host machines. So coming to the software model used in the digital backend. So there is a main thread which runs two subthreads, which is one for the data acquisition and another for the correlation operation. And the correlation processing again opens another 4 parallel threads, one for reading the data from the shared memory, one for the sharing, MPI sharing of data between the different compute nodes, and one for the actual correlation processing within the GPU, and the last thread for writing the final visibilities to the disk. So the hardware used in the digital backend includes 16 Roach boards. So these Roach boards are basically the FPGA boards based on Vertex 5, and each board with 2 ADC cards. The ADCs, again, we use IADC boards from Caspar, which is a collaboration for astronomical signal processing and electronics engineering. In that, we are also a member of that collaboration, and they provide open the designs are openly available, as well as the design blocks and libraries are available. So there are 16 Dell T630 machines which are used as compute nodes. Each Dell machine will have 2 GPUs of K40 from NVIDIA, and 5 Dell servers are used as the visibility and beam host, and there are another 5 user accessible host machines, and InfiniBand switches and other NAC cards. So this is the ADC board, the Caspar design ADC board, which is a dual channel ADC. There are 2 ADC analog inputs and 1 synchronous trigger input and 1 clock input. It's a 8-bit ADC which has a maximum clock frequency of 1.2 gigasamples per second. In GMRT digital backend, we are using it at 800 megahertz, 800 megasamples per second. And this is the Roach board, which is the FPGA board based on Vertex 5. And these boards have a PowerPC for programming, and each of these boards has 2 ZDock connectors, so it can connect to two of these ADC boards. And the Dell T630 is the compute servers used in the system, with which has a processor, 2 numbers of Intel Xeon processors, and 64 GB of RAM. And they can support up to a maximum of 4 GPUs, each with 300 watts, and has 8 numbers of PCI slots. The GPU used is K40, which has 2,880 cores and a global memory of 12 GB and a global memory bandwidth of 384 bits. This has a peak performance of in single precision of 4.29 teraflops and in double precision of 1.43 teraflops. We use 2 numbers of these GPUs in each compute node. And so the digital backend is arranged in 2 types of standard 19-inch racks. One is the compute rack, which has the compute nodes with the GPUs, and the host rack, which has got the 5 host machines, 4 numbers of beam host and 1 visibility host. And the compute rack has got the Roach boards and the ADCs, each taking 4 analog inputs, and the 4 compute nodes also installed. And we have also 2 spare nodes kept in the same rack. The full digital backend system for the upgraded GMRT is installed in 6 racks, with the leftmost 2 racks and the rightmost 2 racks having the compute nodes, and the middle rack 3 and 4 having the host nodes as well as the user accessible host nodes. So the one of the issues while using this computations using this GPU servers is that the amount of heat generated, because this GPUs, the K40s generate about 235 watts of power, consume 235 watts of power, and the total power dissipation, heat dissipation in each rack with 4 nodes, each with 2 GPUs, is coming to about 4 kilowatts. And we need to go for a cost-effective solution to achieve this. So what we have done is, rather than using a commercially available cooled racks, we have modified the standard racks which are available, and only we went for racks with more depth, server racks with a depth of 1200 mm, and we provided some fans to have a cool air on the front side of the server machines, and the fans in each of these compute nodes take this cool air and pass it through the system, and on the rear side we will have a warm air, hot air output by again another set of fans here. So the full rack is kept on top of the AC duct, which brings the cool air, and this fan capacity is calculated to be about 2 numbers of 600 CFM fans to provide the cooling, because the input air temperature is roughly about 10 degrees centigrade, and we are limiting the output temperature to about 25 degrees centigrade in the normal operation, and this can go up to 30 degrees centigrade without any warning. If it goes above 30 degrees centigrade, it will raise warning in the control room. So these are some test experimental results of the digital backend, which is the GWB. This is done at L band, one of the sub bands, which is at 110 megahertz, and antenna used as a reference is C10. So this shows the cross amplitude spectrum of each of these antennas with respect to C10, and this shows the cross amplitude stability over time for a few hours. So we can see that the cross amplitude as well as the cross phase is reasonably stable over time, and till the antenna was moved away from the source site somewhere here. These are some imaging results for the digital backend. This is actually the first image generated from the GWB system somewhere in August 2012 for 3C4668 for L band at 1280 megahertz for a 100 megahertz signal, and this is one pulsar output in the incoherent array using 8 antennas at 610 megahertz RF frequency. This is a comparison of the images generated using the wideband digital backend as well as the legacy system. So in the legacy system, we are using this software backend, which with a 32 megahertz bandwidth, and the source used here is 3C129, and the wideband backend gives a RMS noise of about 0.2 millijansky per beam, whereas in the legacy system, it is RMS noise is about 1.8 millijansky per beam. And similarly for the comma cluster, the wideband backend gives an RMS of 28 microjansky, whereas the legacy system about 350 microjansky at 325 megahertz. So now we will have a quick look at the time and frequency standards. So the time and frequency standards are very important for generating The frequency standards are used for generating the local oscillators as well as for generating the clock signals for digitizing the data, sampling and digitization. And the timing standards are needed for recording the data and timestamping, and also needed for time synchronization of the telescope controls at each of the antennas, and also for VLBI observations, accurate time and frequency reference clocks are needed at each station. So in the legacy system, we were using the rubidium oscillator as the reference, as the standard, and now we are using an active hydrogen maser. So this is a simplified block diagram of the time and frequency system. We have an active hydrogen maser, which is used as the frequency standard, which gives a 10 megahertz output, which is given to all the local oscillators in the analog backend. And it is also used to generate a 800 megahertz in a signal generator and distributed to all the A to D converters in the digital backend. The 1 PPS from the GPS 10 GPS rubidium system is used as the timing standard, and that is given to the digital backend for as a trigger signal. The 1 PPS is also used for locking the time to a NTP server, and all other computers in the system, including the online system and the other computers in the digital backend, they are all locked to the timing from the NTP server. So this is a quick comparison of the phase noise and Allen variance of the GPS discipline rubidium as well as the maser unit. The maser which we are using is from T4 Science. Its model is iMaser 3000. This is the active hydrogen maser, and the GPS discipline rubidium is GPS 10 RBN. So that the rubidium gives a phase noise of about minus 95 dBc per hertz at 1 hertz, whereas the maser gives minus 125 dBc per hertz at 1 hertz offset. And the stability is 2 into 10 power minus 11 for over 1 second for the GPS discipline rubidium, whereas it is 7 into 10 power minus 14 over 1 second for the maser unit. We use 10 megahertz as the reference frequency reference, and 1 PPS as the time standard. These are the measurement results of the stability of the rubidium. The measured value is minus 5 into 10 power minus 10 at 1 second offset over 1 second, and phase noise measurement is minus 95 dBc per hertz at 1 hertz offset. And in case of maser, the stability is measured with respect to another maser at the factory, and it gives about stability of 5 into 10 power minus 14 over 1 second, and phase noise of minus 124 per dBc per hertz at 1 hertz offset.
So another question with regard to the previous slide.
Yeah.
Since you your frequency stability measurement for the hydrogen maser is done at the factory.
Yeah.
What do you know about the long-term stability once the device is in your hands?
We have done a measurement here with a time transfer system which was installed with the help of ISTRAC. That was done in 2019. So
that is to say, you're using a frequency standard which ISTRAC provides you in some sense as a reference. Is that right?
No. This was only an experimental setup which was there at GMRT for a few months. So we tested this system in comparison with the ISTRAC time standards. And after the experiment, this was taken away. Now we have a plan to install it at a later date as a permanent arrangement.
Yeah, thank you.
Yeah, so these are the other parameters of the maser, like the output power of 10 dBm, 10 megahertz is 12 dBm, and harmonic, second harmonic is minus 53 dBc, spurious minus 90 dBc. And the maser is actually installed in this room, which is a RFI shielded room with inside a heater cooler box to maintain the temperature within plus minus 0.2 degrees centigrade. And the GPS disciplined rubidium units are installed in this rack, which is sitting behind. There are two GPS disciplined rubidium units. One has the master, and the other is a standby installed there. So we also have a temperature and power monitoring and management system for the maser room, because the maser cannot be powered off for even a short duration. So then the power up, if we have to power it back, it is a big process. So we have put two UPS with a static switch, so that even if one UPS fails, it will automatically switch over to the second one. And in addition to that, we also have a battery pack, which will take care of the maser up to 24 hours. And we also have two wall mount ACs for cooling, and the maser itself is installed inside a heater cooler box, which was provided by the supplier, the maser supplier. And it provides a temperature variation of plus minus 0.2 degrees inside the cooler, heater cooler box. And also the room is a completely RFI shielded room with, we have also provided rubber gaskets for reducing the vibrations on the maser unit, and also with separate isolation transformers and earthing arrangements to take care of the maser unit. And we have a full monitoring system which monitors all parameters of the maser as well as the other environmental parameters inside the room, and which can be also viewed on any browser from either NCRA or GMRT computer network. And the two air conditioners, wall mount air conditioners, are connected in such a way that each of them operate for six hours in a day, 6 hours, and then it switches to the second unit, and like that. So the compressor current of the AC is also monitored, as well as the ambient temperature inside the heater cooler box is also continuously monitored. And we also have facilities for generating a warning signal whenever any of these parameters goes beyond any threshold. Also, for the overall backend system, we have provided monitoring system which provides a spectrum monitoring for the analog backend output. So this is the spectrum which is going to the ADZ for digitization. There is a 60:1 monitoring which collects the spectrum, and it is available. And also this is the spectrum of the final digital backend. In addition to this spectrum monitoring, we also have monitoring of the power level using a power diode detector at the digital backend, at the analog backend. So for all 30 antennas, we have also temperature monitoring at each plug-in unit in the analog system, as well as each rack in the digital backend. So we can see that here, these are the temperatures in the 6 racks within the digital backend. The 4 compute racks have higher temperature, roughly about 25 degrees centigrade, whereas the host nodes, the power dissipation is very low, so the temperature is about much lower in both the host racks. And also we monitor the temperatures at each core of the compute nodes, and all this information is again available on a web browser from the NCRA computer network. So we will now go to some of the current activities in the digital lab. So one of the main issues with broadbanding and improving the sensitivity of the system is interference. We also have a lot of radio interference in the past few years. So there are 2 types of interference. One is the broadband interference, which usually generated from either spark plugs or any sparking in power transmission lines or corona discharge, etc., or a narrowband interference, which is caused by some communication systems or mobile phones and all. So currently we have made a filter, digital filter, which detects and filters out the broadband interference. And that has been implemented in the FPGA immediately after the digitization of the data. Before packetizing, it does the filtering and removes the possible RFI affected samples. So this filtering is done by calculating, deciding on a threshold, which is calculated based on median absolute deviation of a block of data. And then once the threshold is decided,
Ajith?
Pardon me?
Ajith, can you hear me?
Yeah, I can hear you. I can hear
Ajith,
you.
can you hear me?
I can hear you.
You can temporarily switch off. You can switch off your video temporarily. Yeah. Your video, Ajith, you switched off your mic. You can switch off your video because your bandwidth is not good enough.
Okay. Oh, is it okay now?
Yeah.
Okay. So, so the threshold is calculated based on the median absolute deviation of a block of data. And then from that, every sample is compared with the threshold value, and any sample which crosses the threshold is detected as a RFI, and it is replaced with, again, there are different options for replacing. We can either replace it with a constant value or digital noise, or with the threshold value itself. So this has been implemented, and this scheme has been released on a shared risk basis for observations. So it is an optional facility for the user. One can turn it off if it is not needed. And since the in some instances we have observed the RFI to be longer bursts. So instead of directly using the median absolute deviation, we are using a median of median absolute deviation, which is basically MOM. And in case of GMRT digital backend, we are using, we are taking 16K MAD values and then take a median of that. And that is used for calculating the threshold. So this image shows the effect of RFI filtering on both beam output as well as the correlator output. So the two antennas are used in this experiment, C9 and C11. So the red curve is actually the unfiltered data, and the blue curve is the filtered data. And the panel on top is the beam output. And one can see that most of these RFI instances have been filtered out in the blue curve. And similarly for the correlator output, again, we can see that the cross correlation amplitude is plotted over time. And the RFI instances, most of them have been filtered out, and the filtered curve shown by the blue graph is much more cleaner compared. Now, so to look at the effect of this RFI filtering on the image output, so these are some tests done using some 14 antennas in 550 to 850 band with a 200 megahertz bandwidth and 2K channels in the FFT. So the unfiltered data has a RMS of about 1.6 millijansky per beam, which improves to about 0.52 millijansky per beam with the filtered data. In case of imaging, and similar results we get for a beam output also. So this is for a beam output. From compared to the unfiltered data, the filtered data provides a improved SNR of the pulse profile of about 60 to 240.
A question here.
Yeah.
How do you know that the RFI filtering scheme that you're using is not introducing its own artifacts?
Actually, we have not directly observed any direct effect, And we are still doing tests at various threshold levels to confirm this. So that is why we have not released it in the final as a final release. We have only put it as a for experimental purposes on shared risk basis.
So more abstractly, my question is, how would you convince yourself eventually? What scheme would you use to convince yourself that there are no artifacts introduced by the RFI?
Sorry. See, we have compared these images, and from our general measurements, we find that the RMS is improving and the images look better. And we have also done experiments from the engineering side, which show that the signals, any interfering signals are removed. So far, we have not seen any effects, but some users still have some doubts. So that is why we have released in the shared risk basis so that more tests can be done to confirm whether there is some problem. And separately, we are also doing monitoring of the RFI on a regular basis to check the statistics and adjust these parameters we use for this filtering to improve its effectiveness. Is that what?
Well, yeah, I don't know. I mean, since this is very much an experimental situation, I don't suppose you have a very tight answer at the moment to knowing whether or not you're introducing artifacts.
Yeah.
But yeah, thank you.
So I think I guess if I could just make a comment, I think one of the things that's sort of checked is that the various statistics of the signal to see whether any untoward behavior is seen in the statistics of the signal, whether it is in the correlation between different antennas or in a final output like a image or a signal train as shown here. There's also ways in which you can compare these images or outputs against standard templates to see whether they actually match with that or are there any artifacts that are seen. Some of that has been done, some of it is ongoing.
The standard templates then, Yashwant, would depend upon somebody else having done something which is even more sensitive than yours?
Yes, I mean, so it is always bootstrap. So you say, well, here's what this particular source or this particular output should have looked like. And am I getting that, or am I getting something which has some unwanted features in it compared to what it should look like?
Have you tried the following, that you have a sequence of signal where there isn't much RFI, and in that situation you put on your filter and you ask for comparison of the beams that you get or the images that you get between the two situations where RFI is off and the RFI is on? What I'm saying is just the process of filtering, does it produce any artifacts? That's the bottom line question.
That has been, I mean, this is actually, these are examples of RFI. I mean, see, the situation where RFI is off completely on that source is what that ideal image looks like.
Okay, so let me just clarify what I was. RFI off is actually that you don't have any bursts of interference.
Yeah.
And there is another off and on over here, which is filter off and filter on.
Yes.
So in a situation where there's a time, a time series, which is free of RFI in the sky or in the pickup or whatever, and then you have the filter off as well as the filter on outputs from that situation, and you can compare those two.
Yes. And to some extent, that's what I meant by just looking at the statistics of the filter on situation to see that they match with what you would expect for true statistics. Also, in these situations where what the signal looks like when RFI is off is very easy to obtain. And so here what is shown is, especially in the pulsar signal at the bottom, is the integrated signal. But certainly this has, we have done this, that you can split this into parts where the RFI is not there and into parts where the RFI is there and has been removed by the filter, and ask that, do I see the same statistical behavior of the signal? That kind of thing has been done. But then, it doesn't cover all possible instances of occurrence of the RFI. For example, if it is very strong, then what does the filter do, and so on. But to some extent, that has been done.
Okay. Thank you.
Okay. Yeah. So,
Okay.
Yeah. Okay. Thanks. Another modification which was recently implemented is replacing the original digital backend filtering was channelization was done using normal FFTs, and we have replaced them with polyphase filter bank recently. And so this reduces the spectral leakage and other issues for a normal DFT. So compared to a normal FFT, which needs n samples of data for an endpoint DFT, in case of a PFB based channelizer, we need P into n times samples. So we need more processing to be done in the system to provide better isolation between the adjacent channels. So here the n into p samples are taken and they are multiplied with a window function of n into p length, and point by point it is multiplied, and then the resulting samples are then divided into p subsets, each of length n, and the corresponding time samples, corresponding points are then added, and to get a final n point samples. And these n samples are then passed through a normal endpoint FFT. This is what has been implemented, and this system has been released. So now coming to the total compute load, because of adding this PFB is for a 200 megahertz 8 taps system is about 409 gigaflops, and which is shared between the 16 compute nodes. So as we change the number of taps, we need to process more and more data, and it will improve the performance of the PFB. We have done an experiment by giving a CW signal to the system and changing that number of taps. So the red curve is actually with the no taps. Basically, it is only the FFT, so and without any taps. And as you go to, then the experiment has been done with 4 tabs, which is shown in green color, and then 8 tabs, which is shown in blue color, and the 16 tabs in magenta color. So as we increase the number of tabs, the spectrum becomes more and more narrow, and the whole power is indicated at the correct beat. So this has been implemented and is released for use. So another development in progress is implementation of Welsh scheme. This is needed for removing any crosstalk between different signals from different antennas, and especially at the central station antenna, signals from all the 30 antennas are coming to a same room and it is processed. So there is a very high chance of crosstalk. And so what we have is a Welsh pattern generator at the antenna base, which generates a unique pattern, and that is sent to the front-end electronics where there is a phase modulator. So this pattern is used to phase modulate the signals, and then the corresponding demodulation is done in the digital backend after the digitization in the FPGA. So so there is another Welsh pattern generator which generates the same pattern as the antenna at the central station, which is used for the demodulation. So what is important here is the pattern generator at the antenna and the pattern generator at the central station. They have to be synchronized, and for this purpose, we send a start pulse from the antenna pattern generator, which is used to start the pattern generation at the central station. And this signal is modulated on CW signal, and is transmitted over the return fiber link to the central station. And this scheme is in testing stages, and for GMRT, we will need 60 unique patterns because for which we will need a 128-bit Welsh pattern, and which is generated using a CPLD-based circuit at the antenna base, and at the central station, it is generated using a in the same FPGA for demodulation. And the sequence is transmitted to the central station over the return fiber link on a 105 megahertz return reference signal. And this is currently in the testing stages. So for test, we have used these are lab tests where we have used two independent noise generators, which are totally uncorrelated, and which is passed through the Welsh modulator. And after the Welsh modulator in the receiver, we connect a small amount of common noise in the two channels. And this is connected to the two channels of the backend system. And now we can see the result of the cross correlation between these two channels. When there is no Welsh, we get a cross correlation of about 0.04. And when we add Welsh in either of the channels, the cross correlation drops to almost 0 level. So this is the time series plot, and the corresponding spectrum plot is shown here. This is without Welsh, and this is the spectrum with Welsh. So the scheme is basically seems to be working, and we need to sort out some other issues before we actually go ahead with the implementation. And also, as part of the experiments, we are also testing a phased array feed, and this will be useful for improving the field of view of the telescope. So, and that will increase the survey speed also. So for the GMRT, the plan is to have a focal plane array at 550 to 850 megahertz band in both polarizations, and generate about 30 independent beams with 300 megahertz bandwidth. So for the experimental purposes, we have a focal plane array which is purchased from Astron, which works in L band, and this is we have built the backend for this system. This backend is developed on a Roach board on Vertex 5, and with a 64 channel ADC for the digitization of the data. And two designs are developed. One is a narrowband 32 megahertz bandwidth system, which takes a maximum of up to 32 inputs and generates 5 beams on 1K channels. And also a separate wideband design using the normal IADC boards is also developed, which takes 4 inputs and 2 beams with 256 channels. And this also has been tested, and this is the beam pattern for the beam by radiating a CW signal at 1300 megahertz, and the measured beam width is about 14 degrees for a CW signal. And the same experiment was also repeated using a radiation of a noise signal of 32 megahertz bandwidth over 1300 megahertz center frequency. And with the noise radiated signal, the measured bandwidth is about 17 degrees. So we are still optimizing the design to get the correct weights to be applied before doing the beamforming. So this experiment is still in progress. Now, there are also some other experiments. Yeah.
Ajith, can you please try to summarize quickly?
Yeah. Actually, I have reached the last slide actually.
Okay.
Yeah. So these are some other developmental jobs in the lab which is going on, and like the early digitization, which is to do the digitization at the antenna instead of at the central station and bring the digital signals through fiber. Some initial tests have been done, and we need to do more tests before finalizing it. And also, we are planning to develop a timescale setup in collaboration with this track. Some experiments have done last year, but we need to have a permanent setup to test the And also it will improve the accumulated phase and frequency offsets in the system compared to what the normal hydrogen measure gives. So it will be useful for as a improved time and frequency standard. And we are also developing schemes for recording the samples, digitized samples in the raw data recording, so that the data can be processed in offline. So for that, different options using normal SATA disk as well as NVMe based solid state disks. These are all being tried, and experiments are in progress. And we are also planning to implement VLBI facility, and also a new parallel backend which will process the data in offline by reading data from raw data recorded files, and using new GPUs from NVIDIA like GP100 or GB100, and also newer server machines is being planned, and these tests are in very initial stages. So I think this is all I have. Yeah, thank you.
Okay, so Ajith, thank you for this very detailed presentation about the backend system. Of course, there are good discussion, especially of course from Krishnan. And are there any more questions to you? So people who are on Zoom, please mute yourself and you can ask question. By the time I want to take one question, Ajith, from the YouTube. Ajith, can you hear me?
Yes, I can hear you.
Okay, this is from Aditya. What will be the RFI effects caused by thousands of low Earth orbit satellites, like Constellation being launched by Starlink, SpaceX, and how do you plan to mitigate them?
I am not sure about what is the frequency range of these satellites which he's talking about.
So I can maybe I can just comment on that. That's a good question, but luckily their frequency range is well above the GMRT range. It is a problem that the SKA is going to be facing full on, and the SKA team is looking at it, and they are engaging with these companies which are putting up these constellations to look at various mitigation techniques. But luckily for us at GMRT, given a frequency range, it is not an issue.
Okay. Any more questions? Ajith, can you go to your slide on the digital backend where you actually gave overall thing about the basically the GPU, CPU, and the front end.
Are you?
Yeah, just one slide.
Is this what you are asking?
The next one.
This one?
Yeah.
Okay.
Okay, so these units, I mean, the ADC cards you said are an external to FPGA, right? They're not, I mean, so they're on the board, but they are especially, they're separate boards, isn't it, that you connect to FPGA?
Yes.
Okay.
They are not, that is not the single board. ADCs are on a separate board.
Okay. Yeah. And then you have an FPGA board, which is it taking care of basically two antennas?
Each FPGA board will basically take care of 4 channels.
Okay.
Actually 4 antennas, single polarization channel.
Single polarization. Okay. And so therefore you kind of require 8 into 2 such boards,
yes.
Right?
We need, the FPGA boards we need 16, and ADC boards we need 32.
Okay. So again, similarly for on the GPU, are they also, these are commercial boards, or are there something developed here?
GPU, no, we are using.
I mean, chip basically, but I mean, is it an integrated board that you kind of buy and configure, or how do you?
It is a. You are talking about GPU, right?
GPUs now, huh?
Yeah. GPUs. It is the commercial product from NVIDIA, K40.
That is what
we are using.
So, but then
we are doing mainly the configuration and programming of.
Okay. So once again, now when you take each of the system to again backend compute nodes, you will have another layer of packaging, right? For see this from this system you are saying to compute nodes and to host nodes.
Yeah, the host, when I say host node, that is the nodes where the final visibility and beam is getting recorded.
Okay.
That is mainly like a storage.
Storage, okay. But from
it may do a final level of integration and then storage. That's all.
Whereas, so from yeah, please go ahead.
Yeah, so the compute nodes are the T630 machines from Dell.
Correct.
Where each node has got 2 GPUs.
Okay. Got it.
Yeah. So they receive data through the 10 gigabit Ethernet cards, and the data sharing between the nodes is done through this Infinity band. 40 gigabits.
Okay. Thanks. Okay. I think are there any questions to Ajith? If not, so on behalf of all of you, let us thank Ajith for very exhaustive and very nice talk on covering the entire backend. And we can again look forward to the next talk in the series that is going to be in the coming week. With that, thank you everybody. Thank you very much for joining this. Thanks, Ajith.
Okay, thank you.